Hi, myself Professor G. Hemalatha, Professor in the Department of Electronics and Communication Engineering, KSRMCE. Now I would like to discuss about efficient extraction of visual evoked potentials from noisy background EEG. So before going to that, what is the evoked potentials? Let us first discuss what are the different types of biomedical signals. Evoked potential is one of the biomedical signal. Actually, what is meant by signal? Signal is nothing but a single valued function of time that conveys information regarding state or behavior of a system. Okay, as the system can be anything, either an industrial system or any physiological system. If the system is a human physiological system, then the signal is called as a biomedical signal. Processing and extraction of biomedical signal is very important in present days to find out the health disorders of a human man. Actually, in the past days, in the earlier days, there are some skilled physicians are going to observe the time domain signals to find out the any human disorders, health disorders. But present days, there are number of signal processing techniques are available to process the signal, to process the biomedical signal and to obtain the information regarding the health condition of human man. So now here we are going to discuss various types of biomedical signals. There are some important biomedical signals. They are ECG, electrocardiogram, EEG, electroencephalogram. The other is the EMG, electromyogram. So these are the important biomedical signals. Now we will discuss what are the applications of these different biomedical signals and what is the activity of these biomedical signals. First, if we consider electrocardiogram, actually the electrocardiogram is going to give the electrical activity of heart. Electrical activity of heart, that is this electric activity of heart is measured by placing the electrodes on the human body surface. This electrocardiogram gives the condition of the heart, whether it is going to used to identify the health disorders corresponding to the heart. That is heart attacks, it is used to find out the earlier information regarding the heart attacks and any blockages in the arteries. These things can be identified by using the electrocardiogram. An example of electrocardiogram is shown in the figure, where actually it is characterized by the three peaks called PQ, RS, and in this ECG waveform is characterized by the peaks and the time interval between the various peaks. If there are any heart electric arrhythmia, then there will be difference in these peaks and there will be difference in the time segment between these various peaks. By observing this, by processing this ECG signal, we can identify the various health disorders corresponding to the heart. The another biomedical signal is electroencephalogram, EEG, which is going to give the activity of the brain, where this electroencephalogram is measured by placing the electrodes on the scalp. These electrodes are placed according to the 10-20 international system. The various waveforms, various activities regarding to the brain can be identified by using this electroencephalogram. An example of this electroencephalogram is shown in the figure. Actually here this electroencephalogram, these EEG waveforms vary depending on the mental condition of the patient. If the patient is doing some activity and he is active, then we are going to have the first type of waveform. If the patient is not so active, then we are going to have second type of waveform. If the patient is in the sleep condition, we are going to have third type of the waveform. If the patient is in deep sleep or it's a coma condition, we are going to have the fourth type of waveform. In this way, based on the brain condition of the patient, we are going to have different types of brain waves. These EEG waves are also called brain waves. Why? Because these are recorded from the electrodes placed on the scalp, which are going to give the activity of the brain. So these are the one of the biomedical signal. The other type of biomedical signal is the electromyogram EMG, which is used to find the electrical activity of the muscle. The misfunction of the muscles or nerves and can be obtained by using this type of EMG signal. So, where the electrodes are placed on the muscles and these type potentials are measured, and this is called electromyogram. So, these are the important biomedical signals which are more frequently used to find the various health conditions of the human body. Evoked potentials are voltage fluctuations in the EEG in response to the stimulus applied. We can consider the evoked potentials as the time locked synchronized activity of group of neurons that will be added to the EEG of the signal. It can be also considered as electrical response from the brain or brainstem which is obtained from the different type of stimuli. Based on the type of the stimulus we apply, we can have the different types of evoked potentials. They are auditory evoked potentials, visual evoked potentials and somatosensory evoked potentials. Auditory evoked potentials are obtained for the stimulus of auditory stimuli. Visual evoked potentials are obtained for the visual stimuli, and somatosensory evoked potentials are obtained for the somatosensory stimuli. Coming to the applications of evoked potentials, the different evoked potentials are applied in different conditions, different cases. If you consider auditory evoked potentials, which is used for the finding whether the information is propagating between the acoustic nerve in the ear to the cortex or properly or not. Similarly, visual evoked potentials are used to find the retinal and visual disorders. Similarly, somatosensory evoked potentials are used to find the disorders in the sensory paths. So, we can apply the evoked potentials in the various disorders to find out the various disorders. And coming to the visual evoked potentials, which are where the stimulus is visual evoked potentials are obtained by applying the visual stimuli. Coming to the characteristics of visual evoked potentials, the amplitude ranges from 0.1 microvolt to 10 microvolts. But whereas the background EEG amplitude is varying from 10 microvolts to 100 microvolts. So, the main task is to extract these visual evoked potentials which are having the very low voltage from the noisy background EEG. EEG is considered as the background noise. So, we have to extract the evoked potentials from the EEG which is in the range of 10 microvolts to 100 microvolts. Now, let us discuss about the measurement of the visual evoked potentials. Visual evoked potentials are measured similar to the way of measuring the EEG. How the electrodes are placed on the scalp for the EEG, in the similar way the electrode arrangement is used for the measurement of evoked potentials. And we are going to use the 10-20 international system for placing the electrodes. Middle occipital electrode is placed in the midline, and the distance above the anion is 10% of the distance between anion and an ocean, and usually it is 3 to 4 centimeters in case of adults as shown in the figure. And the stimulus applied here is visual stimuli, and usually the checkboard pattern is used to apply the stimulus, here where the checkboard is reversed for every half second. Now, coming to the characteristics of visual evoked potential, a visual evoked potential is mainly characterized by the 3 peaks. One is the first negative peak arriving at 70 milliseconds, the other is the positive peak arriving at 100 milliseconds, the other is the next negative peak arriving at the 140 milliseconds. The evoked potential is mainly characterized by its amplitude and its latency. Latency means it is the time after which applying the stimulus the signal is arrived. This is called latency. The evoked potential is mainly characterized by these two characteristics, amplitude and time, that is called latency. Next, coming to the what is the noise that is going to occur while measuring these evoked potentials. Let us discuss about the noise characteristics. So, actually one of the main noise while measuring the evoked potentials is the background EEG. We have to suppress the background EEG and we have to extract only the fluctuations in the EEG because of the applied stimulus. So, the background EEG is considered as the main noise while extracting the evoked potentials. The other non-cerebral noise sources are also be considered while extracting the evoked potentials. The examples for non-cerebral noise sources are eye blinks, eye movements, power 50-60 Hz power light noise. These are the various non-cerebral noise sources. These are to be considered and these are to be suppressed while extracting the evoked potentials. Now let us discuss the various methods to identify the artifacts and to remove the artifacts. The various methods that can be applied to identify the artifacts are, first one is ensemble averaging, second thing is clip test, the third is standard deviation test, the fourth is kurtosis test, the next one is correlation test, the next one is mode deviation test. These can be applied and we can analyze, we can extract, we can remove the artifacts in the visual evoked potentials so that we can enhance the ensemble average of visual evoked potentials. Let us discuss the various methods to identify the artifacts and to remove the artifacts. The first one is ensemble averaging. In ensemble averaging, the ensemble of M EEG potentials can be expressed as a matrix of n by m size, where n is the number of samples in each ensemble, in each signal. Actually here we are going to consider, we are going to take m different potentials. By repeating the measurement, we are going to have m different signals, where each signal consists of n number of samples. So that this ensemble of m potentials can be expressed as a matrix of size n by m, which can be expressed as x is equal to x1, x2 and so on xm, where x1, x2, xm represents the individual potentials, and in each potential we are going to have n number of samples. For example, if we consider the ith potential, xi can be expressed as xi of a column vector, column matrix, xi of 0, xi of 1 and so on, xi of n minus 1 with n number of rows corresponding to n number of sample values. So, in this way each potential is expressed as a column vector, and these m potentials can be expressed as an ensemble of n by m matrix, that is x is equal to x1, x2 and so on xm. In this ensemble averaging, the corresponding values of corresponding sample values of the different potentials are averaged. For example, if we consider the 0th sample value, the 0th sample value of first signal, that is x1, and 0th sample value of second potential, that is x2 and so on, 0th sample value of mth potential xm. All these are averaged. So, in this way, by performing this ensemble averaging, that is by adding the corresponding sample values of the individual signals, we are going to perform this ensemble averaging. This is a very simple technique that is used in anywhere in the signal processing algorithms to reduce the background noise. So, here also the background noise, that is the EEG, can be eliminated by performing this ensemble averaging. The next method to remove the artifacts is the clipping test. Usually, if the channel is having any struck-at fault, the readings from that particular channel we are going to have continuous values, that is same values will be obtained from the particular channel if it is having struck-at fault. A channel is nothing but the signal that is taken from a particular electrode. Actually, while measuring the evoked potentials, we are going to place the number of electrodes on the scalp. The signal from each electrode corresponds to a particular channel signal. So, in any particular channel, if there is a struck-at fault, we are going to have the same values repeatedly. The particular values will be repeatedly occurring. In such a case, we are going to have the waveform morphology as a clipped waveform. Waveform morphology will be observed as a clipped one in such a case. So, by identifying the signals which are clipped, we can identify the channels with struck-at fault. And if there is a channel with a struck-at fault, and it is more probability that the nearby channel is also may have struck-at fault. So, if a particular channel is having a stopped fault, the signal received from all the nearby channels is also eliminated from the data set corresponding to the evoked potentials. So, in this way the clip test is used to identify the channels with the stopped fault, and the signals received by the nearby channels is eliminated from the data sets, and so that these are considered as the artifacts. The other method used to identify and remove the artifacts is standard deviation test. Standard deviation is actually the second order movement. So, actually the standard deviation is going to give what is the deviation of a set of data values from the mean value. So, here the standard deviation test is used to identify the artifacts in the visual evoked potentials. So, if there is any artifact that is occurring in these evoked potentials, if an artifact occurs, it deviates much from the mean value. In any signal, artifact occurs, we receive the artifacts that deviates much from the mean value. So, here we are going to calculate the standard deviations for all the signals, and we are going to compare the standard deviations of all the signals with a threshold value. If there is any signal with a standard deviation greater than this threshold value, that implies that there is an artifact in that particular signal. So, that the signals corresponding to all the signals corresponding to that channel, that is all the trials, m number of signals received from that channel are eliminated for the further analysis. So, in this way the main point is here to signal if any artifact occurs, then the deviation from its mean value will be more, so that it is identified as an artifact. The other test that is used to identify the artifacts is kurtosis test. Kurtosis is the fourth order movement of statistics, which is used to identify the transients which are because of noise which is generated while during on or off of a electrical equipment. So, this type of transients can be eliminated by using the kurtosis. The expression for the kurtosis is given by that equation. Here, if artifact occurs in any evoked potential in any signal, then it is going to have the more kurtosis value. So, here we are going to calculate the kurtosis of all the signals, and then all the kurtosis values are compared with a threshold window. If any signal is having the kurtosis outside this threshold window, that is considered as artifact, and all the signals in the corresponding trial are removed for the further process. The other method used to identify the artifacts is the correlation test. Correlation is actually is going to give the measure of the relation between any two set of signals or data. If the two signals or set of data are close or they are closely related, then we are going to have more correlation. The expression for the correlation of two discrete time signals is shown in that equation. That equation is going to give the expression for the correlation of two discrete time signals. If the correlation is more, means the two signals resemble each other very closely. If the signals are different, then the correlation will be less. While measuring the visual evoked potentials, there is more correlation between the signal measured from one channel, that is from one electrode, and from the other channel, that is corresponding to the other electrodes. The two signals are highly correlated. Okay, so here the correlation is used to identify the artifacts in the which manner is, if there is a less correlation between the two signals, that implies there is an artifact. So, here what is the procedure used to identify the artifacts using the correlation is, first we are going to obtain ensemble average of all the signals, that is corresponding to the different trials and corresponding to the different channels. We are going to obtain ensemble average of all these signals. Next, we are going to obtain the correlation coefficient of each individual signal as compared with this ensemble average. Each individual signal is compared with the ensemble average, and we are going to calculate the correlation coefficient. So, as the signals are very closely related, we are going to have large correlation coefficient. If an artifact occurs in any particular case, that particular signal deviates more from the actual signal. So that that signal deviates more from the actual signal means the correlation coefficient will become less. So, if artifact occurs, then that signal deviates more from the actual signal, so that we are going to get less correlation coefficient for that case. So, in this way, by calculating the correlation coefficients with respect to the ensemble average, we are going to compare all these correlation coefficients. The correlation coefficients which are very smaller will be corresponding to the artifacts in the particular signal, and those particular channel signals will be rejected from the further analysis. In this way, the correlation is used to identify the artifacts in the visual evoked potentials. The other method used to identify the artifacts in the visual evoked potentials is mode deviation test. Coming to the mode deviation, which is going to give the absolute values of deviation of mean value of set of data from its mode value. Mode deviation means deviation from the mode, the respective how the individual data set values will deviate from the mode value. So, by calculating this mode deviation for the various signals, if there is any artifact in a particular signal, then for that signal there is a more deviation from the mode as compared with there is more deviation from the mode for the other data set values. So, if the mode deviation is maximum, is more, that is it is outside the threshold window. Here also we are going to calculate mode deviation for all the individual signals, and we are going to compare mode deviations of individual signals with the threshold window. For any signal, if the artifact occurs, then the deviation will differ large, so that it comes out of this threshold window. So, by comparing the mode deviation of individual values with the threshold window, and if any mode deviation value comes out of this threshold window, that signal is identified as an artifact, and that will those channel signals will be removed from the further analysis. So, by applying these various methods to identify the artifacts, that is ensemble averaging, clip test, standard deviation test, kurtosis test, correlation test, and mode deviation test. By applying all these tests, we can identify the artifacts, and by removing the artifacts and by considering the ensemble averaging of all the channels and all the trials after removing the artifacts, we are plotted as shown in the figure. Here in the figure we can observe the two waveforms. One is without removing the artifacts, and the other is by removing the artifacts. By removing the artifacts, we can identify that there is an increase in the amplitude of the peaks. The peak amplitudes is increased, so that by enhancing the peaks, we can extract the exact information, and we can identify the exact health condition. That is, we can diagnose the problems very efficiently and exactly. So, by applying the various tests here, we are enhancing the average of the evoked potentials. Here we are considering the two examples corresponding to the two different patients' age. We are going to consider two different examples for two different patients' age. In these two things, we can identify the improving in the peaks N1, P1 and N2. That is the first negative peak, next positive peak and next negative peak. These are enhanced by applying these various methods and removing the artifacts. Conclusion. Finally, I am going to conclude that by applying these various methods, we can identify the artifacts, and by removing these various methods, by removing the artifacts, by applying these various methods, we can enhance the amplitudes, that is the peaks in the evoked potentials, so that we can use these evoked potentials for the efficient extraction of the signals, and so that it can be applied for the efficient identification of human health condition. Thank you.